Okay, in this last lecture, I will show you the connection between the stochastic control problems and some partial differential equations called Hamilton-Jacobi-Bailman equations. So we discussed in the discrete setting the properties and the characterization of the value function, and we have seen that this value function can be described by this dynamic programming principle. Okay, it gives a characterization of the value function, and once you know the value function, you can afterwards reconstruct the optimal trajectories and the optimal policy. Okay, if you are in a setting where a policy exists, then you can compute it once you have your value function. So this value function comes at the cost of solving this dynamic programming principle everywhere in the space. But it's a nice tool, and it's a very important object in control theory. Now, I would like to show you that in the continuous setting, we can do a little bit better than the dynamic programming principle, and we can exploit this principle to get a characterization of the value function as solution of a PDE. Why is it important? Why is it relevant to characterize by a PDE? Well, the theory of PDE has been developed for decades, and everything we can also bring from this part of mathematics would be helpful. And also, the reverse is true. Actually, once you make a connection between the PDE and the optimal control problem, you can also interpret any, or at least this kind of equations. You can interpret the solution as a value function of an optimal control problem, and sometimes you can bring some new results from optimal control theory to PDEs. Okay, so I will try to make this clear in a moment. First, I will start with the stochastic differential equations. My first lecture was on ordinary differential equations and control on ordinary differential equations. And I told you that some cases, discrete setting is more appropriate to model the optimization problem, and in other situations, the continuous time is much relevant. So here I will show you what is the stochastic differential equations and why is it relevant in some cases. Some examples, and then I will talk about the value function, its numerical approximations, and so on. So I will stop when you are tired. So this is a just ordinary differential equation. Okay, so we have a motion here for this system X. The state is following this differential equation. This is what we started with at the first lecture. And here we assume that this differential equation is controlled by means of this function alpha. Alpha is always a measurable function that takes values in a compact set, just to keep it simple. So what we are interested now is the situation where X is not just a single trajectory, it's a process. And this process follows this motion. You have F, this is what we call the dynamics, or we call it the drift. And sigma is the volatility, and B is the Brownian motion. Okay? So we start with the probability space with the filtration. And we consider this differential equation, stochastic differential equation in RD in this probability space. So what I will do from now is always to suppose that the set of controls is a compact set, and I will assume that this F and sigma, they are continuous. and even they are Lipschitz continuous. So Lipschitz continuous with respect to the first variable uniformly with respect to the second one. Okay? But anyhow, all these assumptions can be weakened. You may have something locally Lipschitz continuous and so on. What I want here is just to have a comfortable setting where this equation admits a unique strong solution. A strong solution for this equation is a solution given by this formula plus integral of sigma x tau alpha, so between S and T. So this is a kind of solution, and a strong solution, it means that this solution is given in this probability space. In opposition to strong notion, you may have a weak solution where you don't start by hanging this probability space at the beginning of your slide, but you can choose a probability space where the solution exists. Okay? So the weakest solution would be somehow dependent on the probability space. Here we have a strong solution. You are given the probability space at the beginning, and you know that you have a solution associated to a control, and this setting is enough to guarantee that. So this kind of results, they are known and can be found in the literature. So now, just to understand a little bit what is the behavior of these differential equations. So I give here some properties that I find particularly relevant to understand what is going on. So what we have is, if, for example, you know your function, if you know your process at time t, and if you compute this expectation, so let me now take a control that is constant. Okay? It's still true in some sense if the control is not constant, but this, if the control is constant, this is absolutely rigorous. And this local property says that if you look at the expectation of your trajectory at time t plus delta t minus x at time t, it behaves like f times delta t plus a small thing. So which means that in in expectation, the variation of your process is proportional to the dynamics f, to the drift. And if you take the covariance of this difference, knowing that at time t you are at x, then this covariance is proportional to what we call the diffusion matrix, and the diffusion matrix is sigma transpose. I remind you that we have just started one. So I remind you that sigma is the volatility, this volatility term. And this appears here in this covariance. So this is the diffusion matrix. So you have the main trajectory is given by f, and then you have some randomness around, and the covariance is proportional to this. So this, I think it's important to keep this in mind. So now there is another property that is also very important, and you remember when we were dealing with the dynamic programming principle, it was very important to know that a trajectory, if you start at time t at a position x, you reach somewhere with your control variable, you have a single trajectory and you reach a final position. Now, if you start later from another position on the same trajectory, then you would reach the same final point. This is the idea we have here, and this is, I told you that this is a very important, your trajectory. It doesn't matter what is your path between t and t plus h. If you know where you are at t plus h, the path is not important. You don't need to keep the whole memory. And here we have the same thing. We have a process, that's true, but at each stop in time, if you start, instead of starting from t and x, you start a little bit earlier from the position you reach at time s, then you get the same position. So this is a Markovian property that I write here. So if you take any function that is a bounded function on the space of continuous functions between t and t plus h. So if you, your function of this phi on x tx between t and t plus h conditioned by the filtration is the same thing if you know the trajectory. I guess this should be t. So if you know where you are at time t, you know where you are going, okay, with the same control. So this is just the Markovian property, which is quite natural in the deterministic setting, and you have it also in the stochastic setting. And there's some simple and standing assumptions, okay? Lipschitz continuity or even local Lipschitz continuity. Okay, so this is what we know about the stochastic, and of course, I didn't write it here, but you have also grand lemma, and you can also have some bounds on your trajectory depending on the data. So all this information are available for example, in the book of Oxendal. So now I consider an optimal control problem in finite horizon. T is a capital T is the final time. And we look at this optimal control problem. It's very similar to what we have studied in the first lecture, apart that now, due to this randomness, in the cost is considered as an expectation. So I know that in many other fields, the expectation is maybe not the best risk measure. But still, here, if you have the expectation, then you can do some stuff. If you don't have the expectation and you have another risk measure, then it depends on the cases. But the most general setting is where you take the expectation. So I'm mentioning that because I agree, I fully agree with the remarks of Thierry Rockefeller that usually it's so the expectation is just one risk measure, and you may be interested in something else. That's completely true. But for my lecture, this is the expectation. This is the kind of risk measure we are considering, and this is the setting where you can say more things. Okay, so the state equation. Control, we have some constraints on the control, and we are minimizing this cost, which is composed of a final cost. Usually we call it a payoff in finance, and a distributed cost. And I assume here again that these functions are Lipschitz continuous. So again, here we are interested in this object, which is the minimum value of the problem. So usually, if you discretize the problem, you may have even the characterization. If you write the optimality conditions, then you may be dealing just with the local minimizers. So here, what we put in this function v is really the minimum or the infimum, okay, depending. And actually, I will make here another assumption to guarantee that my problem has a solution. So you remember in the deterministic case, I told you that if you have this set in the deterministic case, I required fxa to be convex. And I said that if it is convex, then the set of trajectories is compact, and then you have, as soon as you have a continuous cost, you know that you have a minimum. Here in the stochastic setting, I need this part and this one to be a convex set. Okay, the image of A by F and sigma transpose should be a convex set. This is what we need. Yeah, why sigma transpose? Actually, here I did a mistake. It should be sigma transpose too. Anyhow, okay. So we have a control problem that admits a solution, and you have this paper that goes back to '89, where you can find the proof in the stochastic setting. In the deterministic setting is much more simple, and it's a consequence of Filippov theorem. But in the stochastic setting, it's much more elaborated, and you can find the proof here. So what can we do usually when you don't have the minimum? So it depends. Actually, what it is proven, for example, in this paper, is that even if you don't have the convexity here, then you don't have necessarily, you don't have a minimum. So then you have to consider the infimum. Okay? But if you consider the same problem where you convexify, your dynamics, then what is proved in the paper is that the minimum of the relaxed problem is equivalent to the infimum here. And it's the same value. But it's the same value that achieves a minimum in a relaxed sense when you convexify the dynamics. So this is true if you don't have state constraints. When you have state constraints, it's not true anymore. The convexified problem and the original problem are completely different. So this is okay. So just now, for now, we assume that it is convex, and my message is that if you don't have state constraints and if it is not convex, you can convexify. The value would be the same. The value is the same, but the minimum is only in the relaxed space. Okay. Now we assume that we have the minimum. We are in a situation where we have the minimum, and we can now write the dynamic programming principle in this way. So you can, it's like what we had in, you can think about t and t plus h is like a discrete times. So the dynamic programming principle links what happened at time t to time t plus 1, t plus h, and the proof I wrote on Tuesday, actually it works here again. It's exactly the same proof. I wrote it in the discrete case, but it's almost the same. You have just to be careful about the process X, its measurability, and so on. It's just some technical details, But it works in, the idea is still the same. So the value function starting at time t from x is exactly the same as if you start at time t plus h from this position, and you have to add the cost to go from t to t plus h, and the minimum over the whole control of this expression gives you exactly the value function at time t. Okay? So I think by now you are familiar with the dynamic programming principle. That's right? Okay. So this dynamic programming principle can be exploited to raise a Hamilton-Jacobi equation, as I said in the introduction. And let us first assume that the value function is C21. C21 is very strong, usually. So I'm asking C2 with respect to space and C1 with respect to time. So it is a strong assumption, but actually this assumption may be satisfied, and I can tell you why in a minute. Okay? When we will write the PDE and you go back to PDE theory, you can see that you can have this, in some situations, you can have this kind of regularity. Okay, assume that it is in C21. Then in stochastic calculus, we have a Ito formula that says that at any time t and any control alpha, the value function at starting from this position at time t plus h, you can write it like the value function at time t. Oh, sorry, this should be xt, okay? X comes first. And then you have this integral where you have the derivative with respect to time plus an operator that involves the first derivative with respect to x times the drift plus this second order term where you can see the Hessian of v times the diffusion matrix, and you take the TR means the trace of this matrix. So here sigma transpose is a matrix, and this is a Hessian, which is also a matrix. So you multiply the two matrices and you take the trace of this matrix. So basically what's and of course, in this expression, we have a small local mertangle, which is a small rest. And since it's a mertangle, so this term would disappear if I take the expectation. It has an expectation equal to 0. So which means that this Ito formula says that basically the expectation of V V at time t starting from this position minus the expectation of V starting at time t on the position x. So this is t plus h, sorry. It's like a derivative. So if you take h goes to 0, then you find the derivative of v with respect to time plus this differential operator. So this is here. Okay. Yeah. So it can be here alpha, here it should be alpha 2. Okay? So this Ito formula gives something like a differentiation of this quantity. When h goes to 0, you get the derivative of v with respect to time plus some derivatives with respect to space. So think about it. If sigma is equal to 0, for example, this is the standard calculus. If sigma is equal to 0, it means that you don't have any stochastic term. You are in the deterministic setting. And this would be simply Taylor formula. Okay. And now, if the function is c to 1, then what I would do, I would here take this dynamic programming principle, subtract vxt from this formula, and pass to the limit when h goes to 0. Of course, I have here a minimization, but assume that this minimization is, there is no problem, okay? That you are allowed to pass to the limit inside the minimization. So what you get from doing that and using Ito formula is that you get that your value function is solution to this equation that is called Hamilton-Jacobi-Bailman equation, where here you have, you can recognize this is what we have seen in the operator L. This is the terms that come from this Ito formula. And this is the cost because in the dynamic programming principle we had this term. Okay? So this is the contribution of the cost. This is just the derivative coming from Ito formula. And you get that your value function is solution to this system. So if you have just one single control, for example, if actually your system is not controlled, you are just following one process, then you get a parabolic equation. And why I say that you may have a smooth solution, because we know that if you have, for example, this term in PDE theory, we know that if the diffusion is uniformly elliptic, which means that sigma is never degenerate, it's a symmetric matrix, sigma transpose should be positive definite, for example, matrix. If this is the case, then your solution would be smooth. Okay? We know that in the parabolic setting, even if you start from something that is not very smooth, if it is just a Lipschitz continuous, but immediately after this time, your function began to be very smooth, because the kernel of the Hit equation would smoothen the solution. Okay? So this is one situation where the solution may be continuous. At the opposite, if sigma is equal to 0, if sigma is equal to 0, then you don't have this contribution, and what you have is only something like transport equation, advection equation. Okay? And the advection equation is not smooth. There is no reason to smoothen. You are just moving. Okay? You start from a function phi, and you are just advecting the solution. Then there is nothing that can smoothen it. The only way to smoothen it is to have some diffusion. So anyhow, even if your solution is not very smooth, you still have a notion for this equation, and this is called the viscosity notion. So what you can prove is your value function is a viscosity solution to this Hamilton-Jacobi equation. So it is backward because we fixed the final time. Okay? In the optimal control problem, we fixed here the final time is fixed, and we are moving from 0 to capital T. So this is why the equation is backward. Otherwise, if you start from 0 and let your final horizon to be moving, then you will get some information at time 0, and you will have a forward Hamilton-Jacobi equation. And okay, so I said that you have a notion for that, and let us see what is this notion. We can, first I will define what it is, and then I can give some comments. So the way to define this solution of this equation with a function v that is not necessarily differentiable, and actually in the general setting, the only thing you can prove is that v is Lipschitz continuous. Okay? If, for example, sigma may be degenerate if this matrix is not positive defined, then the only thing you have is a Lipschitz continuity of the solution. So what is the meaning that we give to these derivatives? It's not the solution cannot be understood in the case of almost everywhere or something like that, because it's not a good notion. Okay? And we know that it is not a good notion because there are simple examples. If you want, I can show you later. There are simple situations where this notion can be satisfied by many solutions. So we want a notion that is robust enough to select only one single solution, and we want this solution to be the value function of our control problem. So this is how we define this notion. So v is a continuous function. Okay? Now we say that it is a subsolution if we have this inequality satisfied by any phi that is a C2 and such that v minus phi has a local maximum on this point, which means that v should be less than phi up to a constant. So what you do, if your function you know that it is only Lipschitz continuous, you want a notion that here, for example, when it is not differentiable, you want to replace the derivatives with something that is here, just the derivatives of a function that is coming from above. Okay? And for the super solution, what you want is to have this inequality satisfied at each x0, s0, and for any function phi such that v minus phi has a local minimum on x0, s0, which means that you ask this information when you have, for functions that are below. Okay? Okay, why is it like that? I will. So the thing is, for example, if you assume that you don't have the second derivative, it's much easier to understand what is going on already in the deterministic case. So in the deterministic case, you can prove that this set, if I take the derivative of phi at t0, x0, if I take p, derivative of phi such that v minus phi achieves a local max at t0, x0, then this is equivalent to say that p belongs to the to the super differential of the function v. Okay? Actually, what we are doing here if we were in the deterministic setting, for example, oh, doesn't work. So what we are doing is just to replace the derivatives in this inequality. We ask this inequality to be satisfied by replacing the derivatives of v by its super differentials. Okay? So if we are in the second order setting, it's what we call, it's like a second order super differential. Okay? It's a generalization of a second order super differential. And we ask this other inequality to be satisfied by all the elements that are in the second order sub-differentials of the function v. So v is not differentiable. It is only Lipschitz continuous, and as a Lipschitz continuous functions, we can define super differentials and sub-differentials. There are many. The ones we use here is what we call the Dini sub-differentials or super differentials. Okay? So this is the information. This is the notion how we define. Okay, and with this viscosity notion, we can guarantee that the solution actually admits the equation admits a solution, since you can prove that your value function satisfies it. Okay, since it satisfies the Hamilton-Jacobi equation in the viscosity notion, then the equation has a solution. But you can prove also under the assumptions I made so far, just Lipschitz continuity, compactness of the set A, you can prove that we have this what we call in PDE the comparison principle. This is something that compare a sub-solution to a super solution. So the super solution should be greater than the sub-solution. Okay? This is how it should be. Sometimes it is not. You may have a sub-solution, so which means that the derivatives satisfies this inequality, and here you have a super solution where the derivatives satisfy this one, but when you come back to the solution, to the functions themselves and you compare them, you may have the comparison in the way around. Okay? But if you are in this setting, just Lipschitz continuity, compactness, then you can guarantee that any super solution is bigger than the sub-solution. And from there, you get the uniqueness. Okay? Uniqueness, why? Because your value function, actually, as I said, you can prove that it is a solution. So it is in the same way sub-solution and super solution. Take another solution and you play with that. You say, okay, my value function is a super solution, the other guy is a sub-solution, then the value function should be greater than the other candidates. And also, as a sub-solution, it should be lower than the other candidates because it's also super solution. And with this, you get uniqueness. So far, what we have is a strong link between this large class of PDEs, partial differential equations. So now, any equation in this form, any equation where you have the derivative with respect to time and a certain operator h that involves the first order derivative and the second order derivative, if h has this form, then you are safe. You know that it is a Hamilton-Jacobi equation, and there is you should have a control, an optimal control problem connected to this PDE. Okay, so this is the link. So the requirements here to have this Hamiltonian in this form, actually you need just H to be convex. If it is convex, then with Legendre formula, you can write something similar to this and give the interpretation as a control problem. Okay? If it is not convex, then there are some works where the authors show that when it is not related to optimal control problem, then it is related to a differential, a stochastic or differential deterministic game. Okay? But the connection, it's very simple if you know that your Hamiltonian is already in this form. Otherwise, if it is convex, then it's also very simple. Okay, so since we have this comparison principle and uniqueness, then the solution to the PDE is connected to, can be interpreted as value function of an adequate control problem. And also, actually, this viscosity notion is a very convenient framework. When you see the first time, when you see this definition involving the super differentials and the sub-differential, it may appear complicated, but actually it is not. And it's also very convenient framework for numerical approximations, and I will show you later. Okay. Now, what we want to do is not only to solve or to characterize the value function. What we want is to solve the original stochastic optimal control problem. The stochastic original control problems, we want to minimize this cost. So I am interested in the value, but I am interested also in the control that gives me this, optimal value. So how can we do that? For the moment, I focused only on the value function. And we have this characterization. We can play with it. We can approximate the PDE and get an approximation of the value function. But what about the optimal control problem? So we know that its solution to this equation. Okay, so this is just, I rewrite here the Hamiltonian in this convenient way, because I will need it in a moment. So we have the operator involving the derivatives and the cost. And now this is what we call in optimal control problem the verification theorem. So the verification theorem says first that if you take any super solution, then it's bigger than V. This is, you can agree with me, because we have just seen the comparison principle. Okay? The comparison principle says that any super solution is greater than sub-solution. And V as a solution, then it is at the same time sub and super solution. So we have this information first. More than that, if I have this super solution and if I have a policy, alpha hat, that is a minimizer for each t and x, it's minimize this quantity, this operator here, you see, it depends on A. And if, oh, sorry, it's the minimizer, the supremum of minus L, then it's the minimizer of L. If you take the minimizer of this function as a function of A, then, and of course, if alpha hat is a well-defined process in A, which means that it should be measurable process with respect to our original filtration, then, and if you, this equation also now, you plug this control, this feedback control, this is how we call it, it's a feedback, because now it's not only something depending in time that you bring from separately from the problem. No, this is related to at each time, depending on the state, you act according to where you are. So if you plug now this control, then it gives you a trajectory, and it turns out that in this case, if you have such a control, then V is equal to the value function. And this feedback is an optimal control process. Okay? So if you know, so this is if you have a wizard that gives you a super differential. So what is the hope? We don't have this wizards so often. Well, if you know that your value function, for example, is smooth enough, and as I told you, if your diffusion is elliptic, uniformly elliptic, then your value function can serve in this verification theorem. Okay? You can take the value function, compute this operator, take the minimizer with respect to A, and this gives you an optimal policy. If your value function is not very smooth, then the verification theorem requires a super solution that is smooth enough. Okay, C21. However, this theorem can be extended to many situations where you can weaken. This is the original verification theorem. It's quite easy to prove. Now, if you don't have access to this super solution, you still may play with the V. And for example, Merton's problem that we discussed this morning, the value function, it happens to be actually C2. You remember, if you had in mind that the shape of the solution is quite smooth. So from there, you can, and actually people do that in economics, from the value function, they can get the optimal policy. Okay? So, and all this, oh, I'm sorry. I have here some references, but if you are interested in the field, we can discuss and I can give you more information. So one very simple and very interesting case, for example, is this Black and Scholes model. Okay, Black and Scholes in finance is something that related to option pricing. So you have this S is just a misprint. So your value function depends on the first, the initial value of your asset, and you are just in your portfolio, a part of the asset is invested with a secure rate, let's say R, there is no risk, and the other parts of the portfolio is invested in something which is very risky, okay, with the volatility sigma, and assume that here we are just in dimension 1. If you write the framework we just seen earlier, I'm so sorry, this S should not exist here. I don't know why I have here this S everywhere. Okay, I will correct my. Then if you take just this Black and Scholes value, you can show that it satisfies a dynamic programming. So it's quite close to the framework we have just seen before, apart that now we have this discounted factor, which is given by this exponential. But the ideas remain the same. So you can take now, of course, the optimal control problem doesn't always came come as a finite horizon control problem. You may have different situations, but the idea would be always the same. Write first your dynamic programming principle, use the Ito calculus formula, and get the Hamilton-Jacobi equation. Okay? And then you can, first you do it by assuming that your value function is smooth, just to guess what is the good partial differential equation associated to the control problem. And then from there you can use this machinery of a viscosity notion, and you do it once, twice, and after that you are done. You can do it for, I wouldn't say any problem, because there are some situations, delicate situations, but you can do it. So from here, this part, believe me, it's not hard at all. It's the contribution of this discounted here is that you get RV in the equation. So we have the first derivative, the drift is R times x, and the volatility is sigma x, so you get sigma square x square. So in the previous slide I wrote sigma transpose, but here, since we are in dimension 1, then it's just a square of sigma. So if sigma is strictly positive, then your value function is quite regular. And you see this is a parabolic equation. Now each time you see someone talking about a linear parabolic equation, you know that they are related to a stochastic control problem like this one. Okay? So from the, this is just a simple control problem where you have just a single control. Actually, you are not controlling anything. You have just your trajectory. You start from this initial position and you make your trajectory evolve. So the interesting part here is that you get the value function everywhere just by solving this PDE. You don't have to make the trajectory evolve until capital T to evaluate the value. Okay? So you don't have to do that. Another example is Merton's portfolio that we have just discussed this morning. We have this nonlinear equation. Inside you have linear operators, and you take the minimum over alpha between 0 and 1. And here again, the solution is smooth, quite smooth, not like in the linear case, but it is quite smooth. And actually now, if you come back to the theory, you see that this value function is nothing else the minimum of an expectation at a final cost. So phi, the payoff here, it's the final cost. And here in this problem, actually, I am fixing the initial condition and letting the final time to evolve. So, as I said, you fix the final horizon and let the initial time to be to go from 0 to this final horizon, or you do the reverse, which means that you fix the initial condition and then you let move the final time. Anyhow, this value function is also, you write the dynamic programming principle, you use the Ito formula, and you get this second order partial differential equation. Okay, is there any question so far? Are we fine? No questions? Okay, so the next part that I want to discuss a little bit is just how we compute the value function. So we can actually, to compute this value function, we can stop here. Just the dynamic programming principle, I could discretize the time here and compute the value function by dynamic programming formula. We have a recursion formula, people who like the dual stochastic dynamic programming principle, they can play with that also. And you can get an approximation of the value function. Just from here, discretizing. But how to prove the convergence? And actually, the most general setting to prove the convergence, even if you discretize this equation, this dynamic programming principle, the most efficient and the most general setting for the convergence is the viscosity notion. So this is what we can do in the literature. So let me now discuss just some results in the numerical parts. So assume that we have a discretization of time and consider a discrete family of times. We can also discretize the space. Anyhow, you have to discretize both. We have already discussed that. In the control setting, you don't have a fixed Markov chain. So you are computing everywhere, and then you have to discretize time and space. So in the cycle, I will denote V and K for the approximation of the solution at position xk and at time tn. And what can we do? We can look for example, this is one way to look at the approximation is just to mimic, you can try to find a Markov chain with some transition probabilities. Okay? You have to discretize your optimal control problem as a Markov chain. We did that already. You remember when we had, so first we started with the problem on the Markov chain. And then when we were talking about the discrete time control problem, I told you that you have to project on space, get this barycentric coefficients and write everything like a Markov chain, just to go back to the same setting of Markov chain. Here, I'm not saying how to compute this Markov chain. I am just saying what are the requirements. If I want to construct now, if I want to discretize the state equation, if I want to discretize the optimal control problem, I should at least have something that is close to to the properties we had on the differential system. Do you remember these local properties? I started with that. Yeah, this is the local properties about if you take your process, you know that in expectation you are evolving like the deterministic trajectory with some noise due to this diffusion matrix. And now if we want to construct a Markov chain, it should respect the same local properties. Okay? And now assume that I have discretized the, so pi here, it's just a value of the control. I should have put in alpha, and this is sigma, sigma transpose. So now, if you have such a Markov chain that represents the stochastic differential equation, then you can define the value function in a discrete way. Here I assume that the value is phi. I'm sorry, I missed here one term, L, the distributed cost. Okay? We had a distributed cost, then I should So this should be the minimum of our strategies. Pn T, this is the final time, for example. And here I should have expectation of a summation going from n to nt minus 1, L, x, q, pq, plus the final cost. Or if you want, you can just assume that L is equal to 0. I think this is why I removed L, just to keep it simple. You can remove it and put L equal to, so this summation here, you can just erase it, okay? And of course, if you as we did earlier, if you have this probability of transitions, then this expectation is actually just a summation like that. Okay? So you have a discrete now probability distribution, and it's related to these probabilities of transition. So the expectation becomes just like this. And you come back to the Markov chain approximation again. So this this formula now, you know them. Okay, the L shows up again here. This is the vector now. Everything is in a vector form. So now L is a vector. At each component, you have the value at grid points. Okay. And actually, if you show that your scheme is in this form, so if you choose a scheme in this form, and if it is related to a Markov chain approximation that satisfies the local consistency condition, then from a very general result due to Kushner and Dupuis in 2001, you prove that you have the convergence. Okay? It converges to the value function. Okay. Shall I continue or are you done? You tell me. We continue. Okay, thank you. So this is one way to prove the convergence is to show that you have in your scheme the behavior of a Markov chain approximation with some probability transitions that satisfy the local consistency. If you have this interpretation, you have the convergence proof. This is one way. Another way is to define now, to look at in this general form. So, okay, let me put now the scheme in this form. What I'm doing, you see here, it's a Vn equal to minus this contribution. I'm just subtracting both. So I'm subtracting these two parts and dividing by delta t. This is what we do for any function, not necessarily the approximation of the value function. Okay, for any function psi, we take the difference divided by delta t. And if you do that, you say now that what you have to compute is S delta xk tn, the approximation v delta at a time at xk tn, v delta should be equal to 0. Okay? With this notation of this operator S delta, if you go back here, this formula says that S delta for the function v delta is equal to 0. Okay? So which means that The approximated value function is solution to this nonlinear equation, but it is a discrete equation. Okay, this is why I'm writing this. This is the standard form. When you start from PDE, usually you discretize. You don't look at the probability transitions. You don't care about Markov chain. You don't try to do that. What you do is you write it in another equation, and you look at other properties. What are these properties? The first one is, I should probably write it first, is the consistency. The consistency means that what you are trying to solve is very close to your equation. So, for example, it should be the difference for a regular function should be bounded by some h. H is the mesh size. Okay? So you have a partial differential equation, you discretize it, you have something else, and the first thing that you should have in numerical analysis is the consistency between the two equations. This discrete formula that now you want to solve to get the approximation should be close somehow to your equation, otherwise you are solving something else. Okay? So this is the consistency. What you and also you ask other requirements to this scheme. For example, the regularity. What is the regularity? The regularity, it means that this equation has a solution, and this solution, if your original problem has, let's say, a bounded solution, then at the discrete level, you should also have bounded solutions, because you don't want these solutions to blow up. Okay? So this is the regularity, the kind of regularity we need. And the third property is monotonicity. In the setting of viscosity notion, it's very important. I told you that it's very important to compare the subsolution and super solution. This is a very important thing. And the monotonicity actually is the property that gives you that at the discrete level. If you have, for example, U, which is a super solution, and V is a sub-solution, then you should have a comparison between these two sub and super solution at the discrete level. So this is what we call the monotonicity. So monotonicity, regularity, and consistency is what people are looking at if you are using only numerical analysis tools and you are not trying to give any interpretation in probabilistic interpretation. So as I said first, if you have these properties, then you have a discrete comparison principle, which is the first step. You have, okay, if you may have also bounded solutions or anyway regular solutions. And there is also a framework, a general framework, this time due to Barral-Souganidis in '91, where you prove that under these three properties, regularity, monotonicity, and consistency, the solution to this equation converges towards the unique viscosity solution, which is your value function. Okay? So now we have seen two frameworks. One uses this Markov chain approximation, and the requirement is to have a Markov chain approximation with local properties in the same way we had for the original problem. And if you have that, you are guaranteed for the convergence. And this one is more general because actually it's more general because you don't need even to have a convex Hamiltonian. It works for any general PDE. So this is much more general setting for PDEs. But it says the result for our control setting is the same. You get the convergence towards the viscosity solution of the Hamilton-Jacobi equation. And you can do also some error estimates. You cannot expect that much. Theoretically, you don't get a really nice error estimates because your value function is merely Lipschitz continuous, and when you are close to these singularities, you cannot expect even to have something linear on H. Okay? So this is, I think I will skip this part. Yes, and just to now, coming back to the Markov chain approximation, for example, so we know that if we have a Markov chain approximation that is locally, that has these local properties, local consistency, then it would work. So the question is how to construct, how to build such approximations. So this is one way called the semi-Lagrangian type schemes. So for example, if you have a system, so this is like Euler scheme. If sigma I is equal to 0, you can recognize that this is just a Euler scheme. Okay? And now this contribution is the stochastic part. And actually this is a kind of Euler scheme for a stochastic differential equation. So the differential equation here is dx equal to at time s is equal to f x at time s alpha or pi to be consistent with the notations ds plus sigma xs alpha s the Brownian motion. So on a time step delta t, you move in the direction of f with a path with this step delta t, and then from there you create some noise with the proportional to the roots, the square root of delta t. So this is the Euler discretization for this kind of trajectories. And actually here you take I, this is sigma I are just the columns of sigma. So you do that. So you have, you move in the deterministic case, you move from xk to this next position. Okay? Right? This is if you have a Euler scheme. So this is, you move from xk to this part. In the stochastic case, you move from xk to any of those or positions z plus or minus 1. So you have many positions. So this is how it works. So you start here, you evolve with the dynamics f, and then from there you can move in different ways. Okay? And knowing now all these positions where you arrive, you can try to define your probabilities. So this is what you can do. For example, one way to do that is to consider the normalized eigenvalues of the diffusion matrix. And you take the associated eigenvalues. So this is just one scheme, and there are many other schemes where you just extend the Euler formula. So the idea is that the most important part is that you don't have just one single position. Now you are moving to different positions, and then you can play with the probabilities. If you can see it here. For example, you don't need to have a symmetric balance between the positions on the left and on the right. Okay? So you know that you have some stochasticity on this direction because this is a normalized eigenvector of your diffusion matrix. But you can, if it is convenient for you, you can take here a path greater than the other side. Or you can take something symmetric. Okay? So you end up by these probabilities. In these probabilities again, what you have is this lambda that are the just barycentric coefficients. So you see, when you arrive here, this is your grid. The black nodes are the grid. If you arrive here, you may, for example, find the interpolation or the barycentric coefficients with the closest 3 points, for example. And then you have your lambdas here. You can also choose rho j, and you have some freedom to do that. They should be positive weights with a sum equal to 1, just to guarantee that these quantities are really some probabilities. They are between 0 and 1, and if you make your summation, it should be equal to 1. And of course, to get the most importantly is not just to have probabilities, you need also to have this local consistency. And local consistencies, so you have some conditions on this. There is an interplay between the weight you put here, this weight, and also this eta j. So eta j is this distance, okay? And rho j is the weight that you give to this particular move. So now to guarantee the local consistency, everything can be done explicitly, and you came up with some interplay between this rho j and eta j. And if you satisfy these conditions, then you have a Markov chain approximation that is locally consistent. Okay, so it's not a local scheme, and actually for the second order, it's really hard to have a local scheme. I worked also with Frédéric Bonance on some what we call the generalized finite differences methods, but still they are not local. So in the second order setting, it's not easy to find local numerical schemes. So this is the major drawback so far. Otherwise, you have here a quite general way to have a consistent Markov chain, and the theory already stated by Kushner and Dupuis gives you the convergence of the scheme. Okay, some specific, not that's important. Okay, this would be my last slide. Thank you very much for your attention, and I'm ready if you have questions or remarks. No? Okay, thank you. So we can stop here then. Thank you.